Okay, so yes, over the last two lectures we were talking about electrical flows and optimization and maximum flow problem, and well, today we finally do some real work and actually solve something exactly and correctly, right? The way we like it. So just in case you just tuned in, we are solving the maximum flow problem, and well, the definition is as usual, nothing changed since the morning. So we are trying to find a feasible ST flow of maximum value. So we just want to have look at the feasible ST flow is the one that satisfies the flow conservation constraints and doesn't overflow any arcs, and we want to maximize value. Okay, that's still the same problem we want to solve. And today, yes, I will talk about the result that shows us that actually we can. We are breaking this n⁻³ barrier in more and more general scenarios, and now we are just break it in the scenario when we have unit capacity and directed graphs and everything is fine. So the only real constraint here is the unit capacity, and also actually the dependence on the sparsity is not ideal. So for non-sparse graphs, this bound just becomes m, so there is still something to be desired, but well, it would be boring if everything was finished right away. Okay. So this is the result I want to talk about, so let's just get to it. So, and again, the usual reminder, all capacities are 1, graph is sparse, and we know the value of max flow, even though here it will not matter. Here we don't need to know the value of max flow. Okay, so the obvious question, after this 2 hours of lectures, especially the lecture in the morning, is, that's what also Umesh asked, why, you have such a wonderful progress on the approximate and undirected regime, why are we not done? It's like, why we cannot just take this machinery and just apply it to the directed case and be done with it, okay? So, well, tempting answer would be, well, this is about, we are dealing here with directed graphs. Directed graphs are, of course, different than undirected graphs. And in particular, crucially, electrical flows are an undirected notion. Is that this was crucial that the max electrical flows we always compute in the context of undirected graph. Okay, that's very crucial. So that's a tempting answer, but it's not the right answer. And the reason why this is not the right answer, there are 2 answers. Why I will just focus on one of them, which is very specific to max flow. Namely, max flow has this very interesting feature that you can reduce the exact directed max flow to computation of exact undirected max flow. So it's really not about graph being directed or not. The only thing that's important here is that it says exact and exact here. So essentially, once you are able to solve undirected max flow exactly, as opposed to approximately, you already get the directed case for free. Okay, it's really about it's all about just getting the sufficiently good dependence of our running time on accuracy. Okay, so that's the reason end of the game. And once you realize that, then you look back at what we have done for the undirected max flow. So roughly at the very high level, what we were doing is we just had this electrical flow oracle, and then we just use it to interact with our graph to probe its structure by computing electrical flows. And then we use this multiplicative updates routine to sort of put it all together and get an approximate solution. Okay? So now if you know that the accuracy is the key thing, the key bottleneck here that you sort of that you would like to go over, you realize that multiplicative weights update method is a first order method. So it's an instance of a gradient descent, and it is understood that if you use this kind of method, if you only base your if you only look at the first order methods and you build your solution using first order method, then you have to have some polynomial dependence on 1/epsilon. Okay, there is no way around it. Okay, so if you so the obvious thing is that if you want to have a hope on, let's say, log over 1/epsilon dependence on the error, which would allow you to get exact max flow in that case, you have to throw it away. Like this intermediary is just not powerful enough. This is they will not get anywhere if you use that. So you need something new to put in place here. Okay. So once you realize that, then of course there is a vast optimization literature, and you ask yourself, or you actually look in the literature, what is the next bigger hammer? What is the hammer that actually goes beyond first order information about the function that you are minimizing? And then you will quite quickly find a very, very powerful hammer called interior point methods. Okay, in particular, we will be concerned with the following variety of them, but there's a more general notion. And this is a real hammer. Okay, so essentially, you can view it as a powerful framework for solving not only linear programs, but actually in general convex programs. Okay, so you can extend them to various classes of convex programs. And roughly speaking, the idea, how they work is just as follows. So imagine that we have some linear program in this form. So we have mean c.x, and we have constraints, equality constraints, so ax equal b, but also we have non-negativity constraints. And you can convince yourself that you can cast any LP in this form. Okay? So we are not losing anything in generality here. And now, the way integer power method approach solving such a problem, well, what they do is just they look at it, well, they don't look at it, but conceptually you can look at such an LP, and we see that there are two types of constraints here. Okay? And surprisingly, even though it might not look like that, this Ax equal B constraints are easy. So it's like Boyd is saying, he's always saying that, this is just linear algebra. Okay, so you can, like, if it was just about Ax equal B, then things would be good. Sort of what makes this LP hard, difficult to solve is these non-negativity constraints. So these are really the hard constraints here that we sort of need a new machinery to go beyond. Okay, and so the idea behind the method is just the basic idea is just the following. So what you try to do is that you take care of these hard constraints in a different way than just enforcing them explicitly. So what you do, you just drop these constraints, and instead you introduce a barrier term to your objective function. Okay? So this barrier term, essentially, you can view it as a certain perturbation of your original LP. So you drop the constraints, and then you perturb your objective with this term. So this is sum over I log xi, and mu is sort of the extent of this perturbation. And what you can easily see is that essentially this barrier term really enforces that whenever you are inside the feasible region here, so when all the x are non-negative, then it prevents you from ever have any of the x become negative, because the closer you get to the x equals 0, this term becomes it goes to infinity. So essentially it pushes you out of this boundary of the region. So you can, and this is why this term is named a barrier function. Essentially, it just sort of enforces, penalizes you for getting too close to the boundary of your feasibility region, and this way you enforce this negativity constraints implicitly. Okay, so this is the first step, and then you also it's easy to see. Okay, so so first of all, this you have to trust me on that is that if mu is large enough, so essentially when this term takes over, it becomes more important than our actual objective function, then solving such an LP is very easy. Okay, it essentially boils down to finding something called analytic center of our polytop. Okay, and this can be done easily. And the other thing that you can also notice is that as mu approaches 0 from the positive side, then the optimal solution to our LP mu becomes close to the optimal solution to the actual LP you want to solve. Okay, so essentially all we really are looking for is the solution to LP mu for mu being very close to 0. Okay, so this is the observation, and once you have this observation, then it might already you might get a hint how to try to solve such a problem. And what you do is something called the path following routine. Okay, so what you do, well, you start with some optimal or near optimal solution to your LP mu for big value of mu. You can, as I asserted, you can get it relatively easily. And now what you do, well, you try to sort of improve your LP, sort of like reduce the perturbation. Okay, so what you just do is that, given some near optimal solution to LP mu for some value of mu, what you do, well, you try to use this solution to get a solution for an LP mu for a smaller, so for LP mu prime for a smaller mu prime. Okay, roughly speaking, what you can do is that in each step you take your mu prime to be 1 minus delta times mu for some small delta that will be chosen appropriately, and then you use something called Newton's method to compute near optimal solution to LP mu prime, but starting from your initial point being the optimal solution to the LP mu. Okay, so just a couple of comments. So what is this Newton's method? Roughly speaking, Newton's method is just a way of solving an unconstrained optimization problem in which you just assume, so you approximate your actual objective function, which in this case is just c plus x minus this plus this barrier function. You are just approximating it by just looking at the its second order Taylor expansion, and just you assume that your actual function looks like its second order expansion, and then you just solve it directly once assuming that this is the function. So essentially, you can easily see that here we have this Hessian showing up, which is a matrix, and essentially all you really have to do is just solve a linear system in this matrix in this Hessian to get the optimal x if f was of this form. Okay, so we are ignoring everything beyond that. Okay, so this is what Newton's method does. There is some projection because we want to not leave our our constraint space, but this is the idea. Essentially, you just sort of look at the second order approximation of your function and try to optimize it as opposed to your actual function. Okay. And by the way, this is the crucial moment when we start using second order information about our objective function. Okay, as opposed to previous things that were only based on the gradient. Okay. So this is the idea, and somehow the key point why it works is that the Newton method, it has an interesting feature that if your starting point is sufficiently close of the optimal solution to your given problem, then the convergence of Newton's method is extremely rapid. Okay, so all we are doing here is just the choice of delta. It's governed by taking it sufficiently small, so we can ensure that our current solution to the linear program LP mu is close enough to the optimal solution to the linear program LP mu prime. Okay, and just so essentially we want to make sure that our steps are small enough that we always are in the radius of rapid convergence of the Newton's method. Okay,
that depends on the convexity of properties of F. Like.
It depends on the properties of F. Yes. Okay, it actually depends on the local norm of F. But yes. Okay, so it's yes. There is we will try to come up with a number, but in general, it depends heavily. It depends essentially on the Hessian and so on.
Like the eigenvalue of the Hessian.
Not really eigenvalue, because the nice thing is that essentially everything that the Hessian is approximating well, you get for free. So sort of it actually depends on the third order things.
Shouldn't it depend on the spectral gap of the Hessian?
No, it shouldn't. I think the gradient descent depends on that. Like the point is that if this is a good approximation of your function, you will get the optimum right away. So it really depends on the error, which is like in the third order terms. Okay. Does quantum tell you that it should depend on the? I don't know. Maybe there is something I don't know. I'm happy to learn. But the understanding is that it doesn't. Okay, maybe there is okay. What is for sure true is that if this approximation is good, then you will get the optimal solution you must have. Okay, so the whole point is that. It's probably there is some error terms that you have to take care of. Okay, and somehow why this is called the path following routine? Well, this is a very nice conceptual picture. So roughly, what you should look at is so imagine that this is your feasible region. Like this is the AX equals B, and then this red constraint corresponds to imposing non-negativity constraint. And then if this is our cost vector, then our opt lies somewhere here. So, and the key thing to look at is something called the central path, which is just a curve that you get by looking at all the optimal solution to LP mu for all values of mu. So, as I said, when mu is very big, then sort of these solutions they approach something called the analytic center of this feasible region. But then, as the mu gets smaller and smaller and smaller, we are getting closer and closer to the optimum. Okay, and essentially, all that this path following routine is doing is just trying to follow this curve by just approximating in discrete steps. And of course, the whole idea here is that on one hand you want to take big steps because you want to have as few steps as possible. But since this thing can be quite curvy, you don't want to take too big steps, so you are lost and somehow you are losing. So essentially, the point is that as long as you are close to the central path, there is this radius of rapid convergence for Newton's method. So you don't want to wander too far on, but on the other hand, you want to take a big step. And this is the underlying fundamental tension that you have to understand to understand the complexity of this method. But this is the whole outline of this method. Like all the path following methods work within this framework, and then the question is, how do you take steps, and so on and so on.
The path is an attractor.
Sorry?
The path is an attractor.
Yes. Yes.
What would go wrong if you got too far away from the path?
Well, the problem is that then you lose the rapid convergence of the Newton's method. So essentially, yes, you can go back to the central path, but it will be too expensive. And somehow, like the question is, you want to, the question is, you can take big steps, but then coming back might be so expensive that taking this big step was not really beneficial. Right? We really want to be within the radius of this quadratic convergence of the Newton's method. Once you are below that, then you are in trouble because the convergence becomes much bigger.
So are the blue arrows on this picture steps of the Newton method?
Sorry?
Are the blue arrows on this
yes,
picture?
well, pictorially, I guess. But yes, that's exactly what I'm doing. So essentially,
okay, shouldn't they visit the path?
That actually is a little bit of artistic expression here. So essentially, the way that we will be doing it, so we will take a step, and then we will go back to the central path, and then we will take a step and go back to the central path, and so on. So actually, each arrow is corresponds to two steps. That one of them goes a little bit towards well, on the tangent of this central path, but then you go back to the central path and then you take a step again. So I guess my PowerPoint skills are not strong enough to really express that. So, and also this is a nicer picture, so that's why this is the video. But you were right. The actual thing is that we take a step and then we want to go back to the central path and take a step and so on. Of course, being in the neighborhood of central path is fine. You don't have to be exactly in the central path. Actually, we will never be on this exactly in the central path. Yes.
Is there a sense that log is the right function?
Sorry?
Is there a sense that log is the right function as a variable?
That's a good question. It's completely not clear if it's the right function. Like it's definitely nice. It's like self-concordant and so on. Like it has this property. It's not the only function with properties. I think there are well there are some like some people consider different different barrier function, and because it's all at the end of the day, it's all about the curvature of the central path. That's it. Whatever central path you get, it will be good as long as you can efficiently take a Newton step with respect to this, and and make a good progress. If it was a flat line from x to opt, then it would be great. Actually, you can imagine some like polynomial barrier function for high enough polynomial that will make this thing very straight, but then optimizing over it is very difficult. So there is some trade-off. So definitely, it's not clear that log is the right function here, but somehow people try different things, and log turns out to be usually the best choice here. But it's a very good thing to keep in your back of mind, just thinking, how about a different barrier function? There's definitely, like, we know what are the properties that we need for this to work, but log is not the only function that satisfies it. Okay, any other questions? Okay, so this is the general outline, and once we have this hammer, so let's try something simple. And well, after all, max flow definitely can be casted as an LP. So how about casting max flow as an LP? Just solving it using the method. It's an amazing method. So maybe this will allow us to just get down very quickly. Okay. So maybe the whole problem was that we just didn't know enough optimization earlier to just solve it fast. Okay. So of course, if you ask someone about that, well, the conventional wisdom will just say that this will be too slow. Okay. And the reason why this will be too slow is that essentially, well, we have to take this Newton's method, and as I said, it corresponds to solving a linear system. Okay, and our ability to solve an arbitrary linear system are pretty weak, and essentially the best we can hope for is something super quadratic. So if just taking one step takes already super quadratic time, then well, there is a hope to beat n to the 3 halves? You're already done by the time you take the first step. However, this is only a conventional wisdom, and particularly was observed first by Dijk and Spielmann, that actually, when you look at the LP formulation of the max flow, and you look at the linear systems that are there, they essentially correspond to Laplacian systems. Okay? And for these things, we actually know fast algorithms, and we can implement each of the Newton steps in near linear time. Okay? So that's a very good news, because now the only question that remains is, okay, so we know that each step we can take it in near linear time. It's the fastest we can hope for. So the question is, how many iterations do we need before we converge close to the optimum solution? And of course, this is a very well-studied question, and it's because it's a fundamental question in the theory of the integral method. And Renegard showed in 1988 that this bound is roughly square root of n. Okay, so roughly the convergence rate is roughly square root of n. Okay, so putting this all together, what you get? Well, you get yet another n to the 3 halves algorithm for max flow. So so there is really something annoying about this 3 halves, that it shows up over and over. Okay. And, well, what can we do now? Well, we can definitely improve the running time of iteration, so the only hope would be to improve this upper bound. And, there is some hope for it, because no one believes that this is the right bound. Okay? No one really believes that this is the right bound. But, unfortunately, there is also no proof that you can do better than that. Okay? So this is one of the most fundamental questions in linear programming. It's like how to improve beyond this square root of that bound.
Any lower bound?
Sorry?
Are there any lower bounds?
I think there are some lower bounds. I think the current candidate is m to the 1/3. This is the right thing, and there are some construction. Like I frankly speaking, I didn't follow this lower bounds. As long as they don't prove m to the 1/2, I'm not that interested. Like there are some very the linear programs that they're using. They are very strange. Of course they just serve the purpose. They just fix that. And the way they prove it, of course, is just they fix a variation of the integral method. because this is just a general framework. You can there's a lot of things you can plan. So they just choose one, and for this one they create a program that makes it.
It's a little bit like this sport of showing that
simplex.
simplex.
Yeah, exactly. This is exactly the same sport, and So it is. But I think that even in here it's even less of agreement. What is the? Yeah, I guess the same is for simplex.
So this framework that it's big, and I forget the Danish guy.
Yes.
No.
No. You mean this lower bands for simplex?
Yeah. Does that have any?
No, this is not.
It's purely.
The other things is about working on the.
Purely
Yes. It's purely for simplex, right? And it's purely for the particular application.
So it's conceivable that the right bound is polylog or something.
Yes, it's conceivable, and of course, again, in practice, it's very fast. Right? In practice, it's very fast. Like, you don't really approach like there is no bad idea.
So why for flow problems is it used at OM?
So essentially, like when you look at what you get, like what's the linear system that you get when you know that your matrix A is actually the matrix that sort of checks the flow conservation constraints. When you look at the matrix algebraically, it turns out to be essentially Laplacian.
Also, once you project, you're in.
Yeah. So essentially, so once you project, you just have to solve the Laplacian system, and this we can do fast. Yes.
So, I mean, it seems it depends on the property of an S here.
The Hessian is simple here. It's just 1 over x squared. But then you have to take a projection on the space A, like on the kernel of A, and then that's where when you write this projection, it turns out to be a regression. Okay, because you have this B transpose and so on. So okay, good. So this looks like a.
So inverting the Hessian is not a problem?
Well, inverting Hessian itself is not. It is very easy Hessian. It's actually a negative math, like it's just 1 over x squared. It's diagonal matrix 1 over x squared. But then you want to, you want
so
to.
it's just for the projection.
Yes, that's for projection.
That's where.
Yeah. Okay. Yes, because like the Barry function is a separable function. It's like essentially just so there is no off diagonal terms in the Hessian. It's just diagonal and they are very simple. But the point is that you want to do the projection. Okay. So it looks like a dead end, but let us leave it like that and just try to get something anyways. Okay. And what I will actually do, I will present you an algorithm for max flow.
There is a question from Luca who asks, is the Laplacian system that gives you the interior point step the same one as the electrical flow? Is it electrical flow?
Spoiling surprises, yes. Spoiling surprises here. So essentially, what will happen is that I will give you a self-contained algorithm, but at the end of the day, what we will be doing, it will be exactly implementing the method. In particular, elliptical flows. I will not say it explicitly too many times, but essentially, elliptical flows are exactly the Newton's that we are taking. So essentially, like, you can forget about your methods now. There will be just, if you forget about your methods, there will be just strange thing called centrality that will show up at some point. But other than that, like, this will be a self-contained algorithm. So I will just use elliptical flows to solve the problem. But really, what it's doing, and this is the way I discovered this, is that I got very fed up with the method because I realized that I don't really understand them. So then I just developed the algorithm on my own, and then realized that's what the interpreters are doing. So that's the way, like, so at least for me, that was the way to understand what's really happening there, by just seeing how it plays out in max flow, and then realize that actually I didn't do anything here. This, like, all that I did can be translated back into the integral method framework, and that's sort of one way of doing it. But in particular, indeed, the elliptical flows are exactly correspond to these projections, like solving this, to taking this Newton. They are exactly Newtons that are exactly the elliptical flows. Okay. And actually, let's not go ahead. Okay, so this is just one slide of the setup. So essentially, instead of solving the max flow problem, what I will actually do, I will reduce it to a certain version of an uncapacitated mean cost flow. Okay, and this mean cost flow is a sigma flow, meaning that actually I allow myself to have arbitrary demodes and vertices. Okay, so instead of having just an S and T and then all the other vertices just having no leaks, now I actually just set up a pattern of demodes of what should be surpluses and deficits at different vertices, and I just look at for sigma flows. So any flow that has exactly this pattern of demodes and surpluses. Okay. And again, now I can forget about capacities, and the only thing is now I have cost, and roughly you can think about cost being 1. They will not change in any significant way over time.
So I got rid of directed edges, but no.
I'm not getting rid of the directed edge. Actually, this is very important. I'm not getting rid of directed edges. So no. So I'm not getting rid of the directed edges. Things are still directed, and actually this would be the crucial thing that this again. These are the non-negativity constraints that are the most difficult parts. So actually, this is something that we definitely can't just give up because we need it. Okay, and somehow, why did we do it? So one reason why we did it is that max flow is essentially a feasibility question, at least in general form. So we want to change into an optimization question. So now we just are minimizing some cost of overflow, and also, we get special structure. We don't have to worry about capacities, and also there are additional things that will come up later. Okay, so but essentially the only point to secure this is that there is no capacities now. The only thing that we have to enforce is that there is non-negativity of the flows on the arcs, which are directed. And now the demands can be arbitrary as opposed to just S. Okay. So now we will solve this mean cost sigma flow instance, and this will be a primal dual approach. Okay. So what will happen? We will just maintain a primal and dual feasible solutions, and then we will sort of try to modify both of them to reduce the duality gap, which is sort of the lower bound on the objective value given by the dual solution, and the upper bound of the objective value given by the primal solution. Okay, so let us just take a moment and think, what are the primal and dual feasible solutions look like in this case. So for the primal solution, this is easy. Essentially, any sigma flow, so any flow that preserves the demands given by the sigma, that also has all the flows on arcs being negative, so it doesn't flow the other way on directed arcs. Then any such flow is a feasible primal solution. Okay. So what is the dual solution? It's just a slightly more complicated. So essentially, dual solution corresponds to embedding of our graph in the line. Okay, and our feasibility condition is roughly that we don't stretch our arcs too much. Okay, so what I'm talking about is just the following. So imagine we have an arc that goes from U to V, and here is its embedding into the line given by these numbers YU and YV. And then what we really want, we want that, if I look at the embedding of the tail and the embedding of the head, then the embedding of the head should not be farther to the right to the embedding of the tail than the cost of the arc. Okay? So essentially, the way I can specify it, I can look at the slack as the difference between how far this can go to the right and how far it is to the right, and this will be the slack, and I just have to enforce that the slack is always non-negative. Okay? So by the way, going to the left of the head, you can go as far as you want. It's all about just going to the right. You cannot get stretched to the right too much. Okay, so this is the dual feasibility condition, and we will always maintain a sigma flow F and embedding Y that preserve these feasibility conditions. We always will maintain them, and then we know that essentially what we know then is that we want to minimize the duality gap. So now when you compute the difference between the upper bound on the objective given by the primal solution and the lower bound on the objective given by the dual solution, then it conveniently ends up being just this expression. So this is sum over all edges, the flow on the edge times its slack. Okay, so essentially again, you have nice separable formula for like each edge contributes to duality gap. This product Fe times Se.
Okay. So the graph is just an arbitrary graph, or it looks like a bipartite, or all?
Yeah, it has some special structure. It has some special structure that we sort of I will just wave my hands how we use it towards the end. Like so, yeah, it has some special structure.
What should I think at this point?
You should think about the pictures like this. This is something like something that you would get from relaxing bipartite matching. Just taking a bipartite graph and taking. Okay, so they all look like that. That you take a bipartite graph. You order everything from left to right, and then you just add such a star that, with that dimensional vector and vertex, and you just add arcs both ways from it to every other vertex. Okay, so this is exactly the kind of picture you should have in mind.
And where are the
This
costs?
has no supply, no demand.
Supplies and demands are here.
No, the guy in the middle has no supply.
Yeah, he's zero. Yes, he's zero.
Where are the costs?
Costs are all one. Think about them all being one.
And the dotted edges are free or not?
No, dotted edges are just these bidirectional edges. They are also one.
The capacity is also one?
There is no capacities.
No capacity,
Oh, right.
just
We just got rid of the element for the
So where do the demands appear in the dual problem?
demands appear like in the objective, right? So when you take the dual, then the right hand side of the constraints becomes the objective. So they are suppressed. So this is nice that once you look at the slack, it's very cleanly just you don't have this demands here. They just simplify and you just have the sum of this things.
Okay. What are the Y's?
Y's is just an embedding of this dual solution, embedding of the vertices into the line. So if I have Y's, then I can compute the slacks. So. Okay,
They look like voltages, but they're not.
They will be related to voltages, yes. Just in general they don't have to, but they will build them out of voltages. Yes, indeed, that's a good analogy. It's like there are sort of voltages. So for flow we have a flows and then we have voltages as a dual concept, and this will be what's happening here. Yes?
So are you solving min cost max flow in general, or,
No.
or with this special structure?
With the special structure. So I'm not solving min cost
okay.
max flow in general.
Oh, I see.
That's very important. I would like to, but I can't.
Oh, okay.
So I'm just solving this particular instance this particular type of instances.
And what's special about it is this special vertex that you
Yeah.
It's a bipartite plus special one.
Yeah, this is bipartite
I
plus.
see.
Like I don't want to go too much into the like they showed
Yeah,
up earlier, and I
that's
don't
okay.
really talk about this much. But there is something about the structure that is very important. Particularly, what's important is that I can get from any vertex to any vertex by a path of Legend mode. Okay, that's actually very important. That's why I added this additional bytes.
I see.
Okay.
So these edges are directed in both ways?
In both ways. So there are copies of edges. Like one goes this, one goes the other. Okay, but this one over here are not. They are only from left to right. Okay. So yeah, so we want to essentially our goal is in every primary dual algorithm we just want to reduce the duality gap. But actually will make our life a bit harder, and essentially we will want to reduce the duality gap while enforcing additional constraint. Okay, and this constraint is centrality, and namely what you want also to have. You want to ensure that at any point of time, the contribution of each edge to the duality gap is roughly the same. Okay, so that we are reducing this contribution of each edge in a uniform way. Okay, so we are making our life harder here, because for primary dual framework we just need to reduce the sum, but actually we want to not only reduce the sum but also want to reduce it in a uniform way. That all the contribution of each edge are going down at the same rate.
So this mu is a suggestive choice or just coincidence?
It is suggestive choice. So essentially, if you look back at what the mu was in the binary function, this is exactly the same mu. And what this condition really means, yes, what the really condition means that maintaining centrality just meaning following the central path. So whenever it is the case that all the products are exactly mu, it means that I am at its optimal solution for LP. So yes, definitely the choice wasn't suggestive. It wasn't a coincidence. Okay, so that's.
So is that true for this specific barrier function?
Yes, it's for the specific logarithmic barrier function with this is what will happen. That's the crucial point. So that's if you think about this as a primary dual algorithm, this is the sort of strange part. It's like, why would I enforce this thing? And well, the motivation comes exactly from the method that you want to be close to central path, but this will manifest itself in some way in this primary dual framework. But again, for the same reason that it does in the here.
You're saying that the optimality condition is that those FESE is equal to mu for all E?
Yes. This is the optimality condition. Like if I have FESE equal to the same mu for all the edges, it means that your optimal solution for that give mu for this value. Okay. Okay. So that's our goal. So question is now, everything is very standard now. So question is, how can we actually improve our solutions? If I have a primary dual solution, how I improve it to get a better solution? Okay. And of course, not surprisingly, the answer will use electrical flow to do that. Again, this exactly will be the Newton steps that we are taking. Essentially, since we are maintaining centrality, then we want to we will take a stepping Newton step, which will be a Newton step, and then we sort of always want to make sure that we are close to the central path. So this is exactly like we are really implementing it in a method here without saying this explicitly. Okay. So how will we do that? So imagine we have our current primary dual solution. And what we will do, the key step here is that we will compute an electrical sigma flow with resistances given by resistance of an edge being SE over F. So know that when I compute this electrical flow, I disregard the directions. Okay, so even though the underlying graph is directed, when I compute electrical flow, I forget about the directions, and I allow the flow can go even the wrong direction. It's fine. Okay, I allow my electrical flow to do that. That's very important, and that's one more reason how you can flow, why you can be able to use undirected electrical flows to solve a directed problem. Essentially, you will see that it will come up, but sort of locally you can treat them as an undirected one. And sort of.
So, what's the interpretation of the sigma in the electrical?
You're just optimized now. So what is electrical flow? It's just you minimize over all the flows with the deficit of F at the source. And surplus of F at the sink, and then zero everywhere else. So you minimize energy over all such flows. Okay. So here is just you extend it differently. So now you minimize over all the flows specified the demands given by sigma. Okay, and you look at the minimum energy solution for that. Okay, as long as sigma makes sense, meaning its coordinates sum up to 0, there exists a solution, and you just look for the solution. And you can just actually solving it with electrical diffraction system is extremely easy, because all you have to do. So previously you just had to solve Lx to get the voltages. You just had to solve Lx equal this vector st, which has +1 on s and -1 on t, or the other way around. Here now you just put sigma here, and you are done. So nothing. It's completely within the framework. There's no extension that you will need here. Okay. So once we compute the electrical flow, we want to use it to update our solution. So we have to do a primary improvement step. And what we do is actually something very, very natural. So we just take a mixing of our current solution, with weight 1 minus delta, and then we mix in a delta of this electrical flow. So clearly, since I took a convex combination, I am still getting a sigma flow out of that. Okay, and then I will have to argue about feasibility still, but let's leave it at that. And now, what is the dual improvement? Well, in dual improvement, of course, we can't add flow to the embedding, but of course now we have voltages. Okay. So what we will just do, we'll just use voltages that are inducing this electrical flow by Ohm's law to update our dual solution. So what we do is that we take our old dual solution, and then we add this factor roughly delta times the voltages given by the electrical flow. Okay, and that's our dual update step. Okay, and this is essentially our algorithm. Okay, well, modulo some step that I will not talk about, but morally this is all that our algorithm is doing. And so why does it work? So one crucial thing about this update step is just the following: is that if I look now, after I updated my prime and dual solution, and I look at the corresponding contribution of an edge to the duality gap after this update, and if I ignore all the terms that are depending quadratically on delta, then magic happens. And it's something magic again, but magic happens. And what happens is that actually my mu prime is just 1 minus delta times mu. So notice that this does not depend on the edge. So what it just shows is that the contribution of each edge to the duality gap just goes down at the same rate. Okay. So clearly, if we're able to just really disregard this quadratic terms in delta, then that's it. Yes, essentially we just keep doing that, and we will have amazing ideal centrality in each step, and we just did some sufficiently large number of steps to get it all the way down to close to 0, and it will be done. Okay, and this is all nice and good. And the reason why, by the way, that this is true is just exactly by the way that we set up. That's the Newton step, right? Newton step, it gets in particular the linear terms right, is because it approximates our function up to quadratic term, and for that it solves it exactly. So the only things that can show up are only from later in the integral series, and that's what is manifested by this quadratic terms in delta, but we are ignoring them. So as long as you can ignore them, everything is everything is peachy. It's like everything just
ignoring higher terms. This is the same as ignoring the need to return to the path, right?
Yes. That's exactly the point. Yes. So if we could, that's exactly the point. If you ignore this, if the stem weren't there, then we would just maintain centrality. So we will be exactly following the central path. So if central path was given by some polynomial of some quadratic curve, then then Newton's step would essentially follow it in one step. So that essentially would be the thing. But of course it's not. It's a much more complex curve. So then there are this. That's exactly like when we try to have a quadratic approximation of our local quadratic approximation of our curve. That's where it will end up. So if you ignore the quadratic terms, it will get this idea, but not really, because this is not these two things are not the same. Okay. So now
one quick intuition. If f of e was fairly low on an edge,
yes,
the resistance would be high, and then v squared over r will be also low, right? So if f is low, f prime will also be sort of low.
Yes. Well, it depends.
I mean, the update will be fairly low also, right?
Not really, yes, because this f class can have a very big flow on this particular edge. Yes, like this electrical flow, there is no upper bound on how much flow is on there. So it might be so huge flow that even after multiplying by delta, it still changes the flow by a lot.
No, but you just get v squared divided by r, right? For the edge, the power contribution of the edge.
Yes.
So v squared is fixed. I mean, the potentials are fixed by delta, right? Or sigma, right?
Potentials are fixed. No, sigma just fixes the modes.
What does sigma flow mean?
Sigma flow means that your flow has the right demands back.
You respect the demands.
Yes.
Sorry, it's current source.
Yes.
Yeah.
Yes. Yeah, it just says, now we have multiple sources and multiple sinks, but it just tells you how much flow is flowing through each link.
So the currents.
Yeah. So ST flow is of course an example of this of the sigma flow, and sigma is equal to this vector that has zeros everywhere else except SMT and minus 1 SS and plus 1. Okay. Yes.
Why does the improvement dual step maintain the slacks are negative?
Maintain what? Sorry.
The slacks as prime.
Well, it's not clear, right? That's what you have to show. It's like this is clearly if you take delta equals 0, then it will, and the question is how big a delta it is. So actually, and the same is true for this thing. What might happen is that this flow flows in the other direction that it's supposed to. So again, if you take too big delta, you might end up losing feasibility because you start f prime will start flowing in the wrong direction. Okay, but in general, after this slide, what should be clear that all that we really want to try to understand is how big delta can we take. So this approximation makes sense, and also we do not lose feasibility. Actually, what is happening is that maintaining this condition is stronger than maintaining feasibility. So what you can show is that if you maintain this, then implicitly you're already maintaining feasibility. So you are not taking delta too much. But yeah, if you take arbitrary delta, you could break feasibility in both cases. So you have to also be guarding that, but just proving this is already sufficient. Because if you have to be close to the central path, it means that you have to be far away from the boundaries of your physics. So this is clearly a strong condition. Okay, and that's what you really have to focus on. And roughly, and this is something that I will just cut short, so once you do some math, and also there's another correction step that I'm just skipping now, but essentially what you can, if you ask yourself, how big delta can you take to not wander off too far from the central path, and in particular not to violate feasibility, then essentially what you get is that your universe of delta should be roughly L4 norm of a vector rho. When vector rho is just the following, it's just, you can just think of it as the following. So you have your graph, okay, and you have your current solution. And you think of the flow in your current solution as being capacities of the graph. Okay? And now you are computing an electrical flow in this graph, and you ask yourself, how much this electrical flow is overflowing this capacity imposed by S. So you can think about this as a congestion vector of the electrical flow F plus with respect to capacities given by the current solution F. So you can just think about this vector rho and this L4 normal rho as just measuring how different electrical flow is to our current solution. Okay, so that's some measure. This you just have to take on faith that this is what you get. And now the only thing that remains, okay, so we know how big delta we can do. It's just governed by this L4 norm of this vector. The question is, how can we bound this L4 norm to get some absolute bounds on delta?
So L4 norm is exactly the quantity you care about. It's not just some upper bound.
It's exactly actually. It's exactly again, you can talk about this offline, but according to your current state of knowledge, this is the best you can, the best bound that you can impose. And this is really what you want.
And do you know that? I was asking if you know the 2 norm of flow.
We can just so how to bound an L4 norm? Well, who wants to bound L4 norm? How about an idea? Let's bound the L4 norm by L2 norm because we can always upper bound L2 norm by L4 norm, and then L2 norms that sounds easier to bound. So let's just think about bounding L2 norm instead. Okay, we can definitely do that. Whatever upper bound to L2 norm we get, it will be an upper bound to L4 norm. So everything is nice. Okay. So how can we bound the L2 norm of this vector? As again, it's not really clear. But now actually is the moment when the centrality comes back. Okay, so for now it was a pain for us to maintain the centrality, but now is the moment when it pays back. Because what it allows us to do, it allows us to tie this L2 norm to the energy of the electrical flow. And the energy of electrical flow is something we can't reason about, as opposed to this vector. Okay, so how does it work? So we know that due to centrality, we know that this product is always roughly mu. Okay, so this is what it gives us once we work out our resistances, which are SE over FE. It means that each resistance is roughly mu over FE squared. Okay, so essentially, again, there is this intuition that FE should think about them as a capacity in our graph. So like FE over squared, like dividing by FE over squared is just the right scaling of each term of resistances to make sure that somehow the congestion behaves the right way. Okay. So this we know that these are resistances once we have centrality, and because of that we can show that the energy of the electrical flow is roughly proportional to the mu L2 norm squared of rho. Why? Well, this is just a simple arithmetic. So what is the energy of the flow? It's just sum over all edges, resistance of the edge times the flow squared. But we know what resistances are, and we have this Fe squared term here. We just we can hide it under the square, so we have sum over edges mu times the exactly what this is exactly the congestion vector squared. So well, what we get is exactly that. This is exactly mu times the L2 mole squared. So this is a great news because bounding energy of electrical flow is something that we can do. Okay, and and how can we bound this energy? And again, this is if I had time in the morning to give the proof that I skipped, you would already know how to do it, but we'll do it anyway now. So how can we? How can we bound this energy? And there is a very easy but very powerful argument that you can do. Essentially, you just repeat something that what happens for an electric as well. So I claim that this energy is never bigger than mu times n. Okay. So how to show that? Well, what I will do, instead of trying to bound the energy of the electrical flow directly, I will bound instead the energy of some different sigma flow. Okay? Meaning our current solution F. What is the energy of our current solution F? Well, it's sum over all edges, resistance times the flow squared. But what are the resistances? There are mu over Fe squared. So here I just get all ones vector, like I get ones in each of these components. So there is m of them, and I just get mu times that. Okay? So this is the energy of the current solution. But how can I now infer something about the energy of electrical flow? Any ideas? Even simpler. The Satish is not allowed to answer. So an idea, how to get from this statement to a bound on the energy of electrical flow.
The electrical is the energy minimizer.
Exactly. Yeah. We just use the definition of electrical flow. That's the crucial way we use electrical flows. We know that over all the sigma flows, well, electrical flow is the minimal energy, but we just exhibited one possible flow that has energy of roughly mu n. So here, this is an upper bound on the energy of the electrical. Okay. And well, that's the way you get the claim. And from that, once you unveil all we did, what you get in the end is roughly a square root of m bound on the inverse of delta. So what we just really did here is essentially we recovered this canonical square root of m bound of Renegade here. Okay? And actually this argument, all that I said is just corresponds to algebraic expressions. And if you just put it back in the general integral, like it makes still sense for general ideas. And what you have just done here is essentially just we recreated in a different way the argument of Renegade of how to get the square root of m integration.
Yeah, sorry. So somewhere in here you made the transition to undirected flows. So can you say something more about how that happened? And
this happened somehow. It's again something I told you during the first lecture is that it is hidden here. So I just said if I take steps small enough, I will be fine. And in particular, I will not lose feasibility. Like if I take it more this step. So essentially, what I did is like one thing that implicitly this centrality enforces is that I have non-zero flow on every arc, and also the stretch is non-zero. And now all I'm saying is that now I am computing, and then the step that is small enough that I will, I will even if I'm going the wrong direction, I will not go the wrong direction too far. So that's exactly how that's what you essentially you are getting here is that you are able to sort of like by scaling things like by keeping this barrier far enough, you are always actually symmetrize your problem and take the local stepping undirected. And this is the crucial thing. That's exactly the point why you can use undirected max flow to solve like this. It's just exactly by being careful about always keeping far away from the boundary, okay, and then taking small enough step that even if you go the wrong direction, it's still okay.
And this is using somehow the special structure.
No. In any way, no. This is general. Like, did I use this special graph anyway? No. So no. Okay. It doesn't even care that it works even for general LPs. It doesn't even have to be max flow for that. There will be a moment when we will use this structure. I will tell you when it happens, but it's not now. Okay. Good. So great job. We did all this work and we got once again n to the 3/2 algorithm. Yeah? So. Wouldn't you get frustrated? Actually, I wasn't because I knew, like once I realized that, I knew what is the problem because you already know what happened for the undirected case. But otherwise I would be very frustrated. So how to go beyond the square root of m iteration barrier? Okay. So let's just look back at our reasoning, all that we did. Yes? So we just used the inequality. So we knew that that the inverse of delta is most L for norm of rho. Then we use the L2 to L2 bounding to bound the L for norm, and then we show that L2 norm is at most square root of m. What you can show is that essentially in our framework, the first and the last inequality are tight. So if you are using only L2 norm, which is what many interior papers do, there's no hope for getting beyond square root of n because it's just not true. Like this vector can consistently be close to square root of n. Okay, then you can construct instances if this is the case. So there's only one hope here. It's try to play with this inequality here. And of course, the crucial question is, when is this inequality tight? So when is L4 norm of a vector close to the L2 norm? Okay.
Only one coordinate.
Yes, but yes, James. Yeah, that's a perfect answer. So like when these things are close, they're only when the norm of rho is contributed, by very few coordinates, actually one or like few coordinates. Okay. So now the question is, okay, so we know now when things go bad. So okay, this is to our setting. This is to our setting. It just means that the things go bad if in our elliptical flow there are arcs that contribute most of the energy. Okay, that's exactly what it means in our language. So is it good or is it bad? Well, it's bad because this actually can happen, right? And we already have seen examples when exactly this kind of phenomenon happens, that there is one arc that contributes most of the energy. Okay, so in this sense, this bound is unfortunately tight as well, and this is exactly the bottleneck. Once you look back to empirical methods, where the square root of n, like this is the barrier, square root of n. Like, so that, but the important thing that again, going a little bit about ahead myself, is that these steps can happen, the bad steps can happen, but maybe they don't happen too often. Okay, so essentially they can be bad steps, but I will talk about more about this. But essentially this can happen. But again, we know what to do. At least we know what we did in the native case. Okay, so what we do is, we try to ensure that if it happens, it doesn't happen too often. Okay, and that's sort of the philosophically, that's if I just gave it that, that should be the end of the story. And unfortunately, the answer is a bit technical, so I will just say a little bit about it, but not too much. Because what we in the end do, we just apply a very careful perturbation to our solution in our LP and set up preconditioning to exactly ensure that whenever this bad step, like that, maybe this bad steps happen, but they do not happen too often. And this is the moment when we really use the structure of the max flow and of our instances, and the fact that we are solving max flow, and the fact that we are using the capacity. So everything up to now is true for general LPs. This is the moment when things require when you really have to dig into the structure to make the argument work. Okay, so let me just say a little bit about what's happening here. So again, the problematic case is when most of the energy of our electrical flow is contributed by only a few arcs. Okay, and how can we ensure that is not the case? So we had similar problems in the directed case, and what we did there, well, we just kept removing these high energy edges. Okay, and then we showed that to show that it works, we just use the energy potential to show that it can't happen too often because energy is growing, and it can't grow too much. So clearly the end. So this was all nice and pitchy there, but the problem is that so that's exactly what's the argument. The problem is that we can't really afford to do this in our framework, right? We want to compute our flow exactly, so just removing edges left and right doesn't seem like a good strategy to get an exact mass flow. And also, the even more significant problem is that in our case, so previously we used energy as a potential, and the nice thing about the energy then was that it was only glowing. Okay, so because we were only using resistances of the edges. Now it's not true at all. Now from step to step, energy can go down or up or down. There is nothing that we can really say about what is the behavior of this energy. So suddenly it just becomes a very awful potential energy because it doesn't go in one direction. Okay, so even though the spirit seems to be right, when you look at the actual what's happening, this doesn't seem to fit. Okay, so how to deal with this problem? So one thing is that first we have to get good potential. So what we do is actually instead of just enforcing a condition that this L4 norm is small, what we ask for something stronger. It's some kind of smoothness condition that I will not talk about. Roughly we try to restrict the whole spectrum of energy contribution of edges. And the reason why we do this is that once we enforce that our flows that we use are smooth, then the energy does not change too much anymore, and it becomes a good potential function now. Okay, but we have to enforce more. But what we get in return is that we get a potential function. Okay, and now the way we enforce this condition is that essentially whenever we see some arcs that offend this condition, we just perturb them. And the way we perturb them is not by removing it, but just by increasing the length of the so we are changing the so we are increasing the length of the arc by their slack, And because of that, this results in doubling the resistance. So essentially, instead of removing arcs, we just are doubling the resistance. Okay, whenever we don't like what some arc is doing, we just double its resistance and we recompute. Okay? And,
It's still in the same spirit.
The spirit is the same, of course.
Increase the resistance to infinity.
Yeah, but the spirit is definitely very similar. Unfortunately, now we have to be much more careful about stuff, right? But yes, I agree. That's why I was talking about this other result in the morning, because it's sort of conceptually, it gives you most of the ideas already. And one nice thing is about that, as long as this perturbation are small, so as long as the SE is small, then we just perturb the cost of our in our solution just by a little bit. So once you get some solution, in the end you can correct any discrepancy, but relatively cheaply. It's sort of this is still fine. So as long as the bad arcs have small stretch, everything is fine. Unfortunately, not all arcs have to have small stretch. So how to deal with edges that have big stretch? So roughly the observation here is just the following: is that one thing that you can say about the edges with SE is that since this is how the resistance is going, then we know that if SE is big, it means that the resistance is big as well. Okay? And now, once you look at edge that has big resistance, and if you ask yourself, what does it mean that this arc contributes a lot of energy in the electrical flow? What it means that it also has a high effective resistance. Okay? So resistance and effective resistance are different things. So if I have an arc that has high resistance and still flows a lot, it means that it's a very high effective resistance, because it means that there is no good way going around this arc. You really have to go through the arc because there is no better way, which means that that's exactly what the notion of effective resistance is capturing. And then what you essentially do to fix that, you precondition your solution in such a way that there is no arc in your graph, in your solution, that has larger effective resistance. Okay? So essentially the way you do it is that if this is your solution, what you do, you just add another sort of star graph here, that somehow, there are some technical things that you have to do, but the idea is that essentially you are adding additional edges just to make sure that there is no two vertices here that have high effective resistance. You are essentially smashing the effective resistance diameter of this graph by adding the star graph just to bound it.
Do you ever change the demand sigma?
No, sort of locally, but in general no. In the end, the solution I get in the end is to the original demos. Locally they change. There is a lot of technical pieces here that somehow are local and they shouldn't be there, but they are. But conceptually, no, they are the same. Yeah, so this is just the way we do this preconditioning. And then once you do that, you can show by appropriate argument that now you never have problems with arcs that have large SE. So the only arc that will give you problems are the arcs with the small SE, which you can deal with by just changing your LP. And in the end, once you add a couple of pages of work, this all comes together and gives you a new result. Okay? So essentially this is all I want to say about this result. James?
So these arcs are just a mechanism of sort of moving this, instead of paying a lot, you get some error in somewhere that you can fix later.
Yes, so nice thing about this preconditioning is that essentially once I do this, these are arcs that do not exist in my original instance. So, and the problem is that, of course, from the point of view of the solution, these arcs are, perfectly acceptable arcs, so there is some flow that will be routed over them. And this is the flow that is working, that is going over phantom edges, right? So, in the end, I have to deal somehow with this, so what I have to reroute this flow somehow. And I just do this, and I only pay with duality gravitas. So essentially, I'm just showing that after, a number of improvements that, I look at the flow that was routed here, and I just, route it back in a less efficient way. But, this increases my duality gap, but then I show that my decreasing duality gap is big enough that this small increase, doesn't prevent my progress. But yes, you have to deal with it.
You have to specifically keep track of the flow.
Yes. So that's exactly the moment when I said that the demos are because you are removing these edges and you see what are the discrepancies in these demos by doing that, and then you just fix these things again. And that's the way. That's the way you do it. Okay.
So is it fair to say that the way this algorithm pushes a lot of flow on particular edges is by blowing up resistance to the rest of it?
What it is doing, it's just it's trying to So what is the big bottleneck? So one nice problem to think of when you try to get better maximum algorithm is just to try to solve the solution for the relaxation of the Parham magic question. Okay? And what is the problem when you use electrical flows to do that? The problem is that there might be one edge that is so tempting for the electrical flows that they flow all the flow through it, and that's a useless solution to it because what you would like is that if you have your resistance, right, so I assume all you know how we relax, like how we can capture Berkeley magic as a max flow. So we are just trying to push some flow from here to here. Okay? And the point is that if you use elliptical flows, what can happen that all the flow of, let's say you know that the matching is of size n, so you prove you want to push n, a value of n flows, that all of that does goes over one arc, and this is useless to you because you know how to you could just take a simple path and push along the one arc. What you really want to have is that it's spread out among many arcs, among many different paths, because that's how you make a non-trivial progress in one step. Okay. So essentially, the problem is that of course elliptical flow doesn't know that, and it can just still keep some arcs to be more desirable, and then exactly you have the stretching operation that increases the resistance to discourage the elliptical flow from doing that. Okay, so that's roughly what is the picture here. Okay.
On the previous slide, what did you mean by increasing the length?
Well, I mean literally. So the point is that when I just want to increase the. Okay, I would need to go all the way around. Let me just draw this. So essentially, when I have my arc, I have this dual embedding, right, of my arc. So here is YU, YD, and somewhere here is the slack, right? And this is the cost. So what I want to do, I want to add plus, SE to the cost, which ends up doubling the slack.
You have unit costs on the.
It doesn't matter. It's just additive. I just usually they use, but as you are stretching things, then the cost can grow. So it's whatever the current cost.
Here you're changing the costs of the.
Yeah, the actual cost. So I'm changing the LP, which is not ideal, but that's the best I can do. But I'm actually changing the LP, not only my solution, but also the LP. Okay.
Yeah. But those. Yeah. So those costs, they were sort of. I mean, were they important or?
They are important. So that's why I said that I don't want this perturbation of cost to be too large, because in the end I want to be able to fix discrepancies between. Because sort of the statement that you can actually prove is that in the machinery that I can solve any LP for you in this m to the 3 over 7 iterations. The problem is that I will solve not the LP you asked me to solve. Okay, so it will be LP with some cost perturbation, and for unit capacity max flow, I can say something about this, how different is the solution to this LP to the original, and I can fix it using augmenting paths. For general LP, I have no idea. Even changing one cost can crucially change the solution. I don't know how to fix it. So I don't know how to do this perturbation in a way that preserves the optimal solution, the closest of the optimal solution to the actual solution of the perturbed problem.
So this augmenting paths is the thing whose analog is missing for the general LP. Is the main thing, or the
sort of? I'm not, well, yes, but the question is exactly the point is, and in general you can solve that this is false, right? If I give you a small L1, if I have the cost in your LP and I just add a small L1, small L1 norm perturbation to all the coordinates, to the costs. Okay. How much, how robust your LP formation is under that? Yes. For unit capacity flow, we know that you are missing at most L1 norm of flow, which if it's small enough you can fix. Already for arbitrary capacities, even one arc might, if it has a capacity of n, is suddenly a much bigger problem. Okay, so that's crucially this is the only way we use unit capacity. That's exactly the moment when we want to actually say something about how much the perturbation hurts us. Okay? And you can clearly see that if you think about LPs, in general, even I think it can really can kill it completely.
So roughly, also the way you're encoding directions is that the asymmetry is that if you flow in the right direction, the stretch is small. If you flow in the wrong direction, the stretch is really big.
Yes, but also on some arcs you want to have big stretch and small flow because the stretch is supposed to do that. It's essentially some arcs you don't want to route flow from some arc and they should get large stretch. So it's not only related to it. That's of course what will happen, but again, it's sometimes the good direction is exactly to remove the flow because maybe that you shouldn't be flowing the flow of the arc anyway. That's what exactly.
There are two different reasons.
Yeah, there are two different reasons. Right? So yeah, so okay, I can tell you more time because I'm over time, but there's yet another way of looking at it. What's happening here at the high level. But okay. So that's all I wanted to say. So let me just as John said, pontificate. So what I showed in this talk and in the previous in this talk in particular is that using elliptical flows for centrifugal method is a powerful new approach to max flow. Actually makes progress on things that we wanted to get progress, and of course the question is, can we go okay all the way? Can we get actually an exact directed max flow solve it in linear time? My bet is yes, and I really think that we have the critical mass of ideas, but somehow, well, it's not yet there yet. But I think we are really converging, and in particular, it's like I also want to just reiterate this point that I think is important to keep in mind during this semester. The one that James doesn't agree with is that I view electrical flows as just the next generation of spectral tools. Okay, so
it's a good compromise. It's spectral tools.
I see. Really, like to me, I'm not sure. Okay, whatever. This makes you happy. So essentially, now once you have this, electrical flows depend on the whole spectrum as opposed to just a few eigenvalues, and they come at the same price tag. Question is, let's look at the classical application of spectral graph theory and see, can we get something better using this, stronger tool, like better spectral graph partitioning, and so on. And of course, already some answers to that are yes. There are some ways. There are some works that use electrical flow and end up having better guarantees than what is given by electrical flows. But yeah, and in particular, we have seen in the random walk generations that using electrical flows, fast computation of electrical flows, we are able to say something more about behavior of random walk than just how quickly the random walk mixes. Okay, so there are some, but of course I think this is just the beginning. And then of course this is just a plugin because I am a graph theory person, so I just want everyone to think, if you have some free time during the semester, it's just there's so many problems in graph algorithms. Can we get linear time algorithms for all? And again, it's less a question of which problem we want to solve. I think that once we get enough tools and enough ideas, how to solve one of the important problems, we'll quickly be able to adapt it to others. So I really think that this is a challenge. Of course, it's a quite ambitious one, but I don't think it's as ridiculous as it might sound at first. And in particular, we have a new, recipe for algorithmic problems where we just take these linear algebraic tools and continuous optimization methods, and we just plug it in all together, and we get something to do. So we already have some ideas.
So do you really believe that every graph
optimization
problem?
Of course I don't.
Okay,
but it's to motivate. Yes, I don't know which one are and which one no. Of course it's not true, but actually, what you can say is that there is a useful notion of approximation for which you can solve. Okay, let that be the escape route for me. But again, this is just a slogan which, as we know in life, we don't really correspond to reality. But you get the idea. Okay, so in particular, there is this amplitude treehouse band that shows up everywhere, and there is quite a lot of problems that got stuck on this barrier, and usually for similar reasons. So these are just some of them, and the question is, can we just take this framework and just finally get rid of this amplitude treehouse band and go all the way to the linear time? Okay, and so in particular, of course, I think the second order methods is a new thing in the blog, on the blog, because previously, and this was the right criticism, was that okay, well, this IPMs, you have to take Newton's step, it's very expensive. That's not a way to get fast algorithms. But now we see that in some cases, important cases, we can solve, we can take Newton's step faster. And now you suddenly become we have a very powerful hammer. There's a lot of things that you can write as an LP. Question is, what can you do with it? So that's something to just ponder. And finally, just one thing that I also like about this, and I think I also would like you to keep in mind is that, okay, so far, we were using, when you look at this optimization literature, we were using it as we were users of that. Okay? So we were just taking, this, we were taking that, and plugging it into our problems, and we get solutions. But now I really genuinely believe that we can also contribute back. Okay, that we can just see that some of the ideas that come up in the specific application of these tools end up being applicable more broadly. So in particular, one thing that essentially you can prove is that even though I have this interpol method and this feed-up for a particular max flow question, in general, what it really tells us is that as I already said, you can solve any LP faster, except this will not be the LP you ask for. Okay, so that's not ideal yet, but maybe it's getting there. In particular, there are some ideas that I think are important, and it might be even new to the optimization, to the optimization community that I think people should realize. So one thing is the interplay of L2 versus L4 norm, but you really have to look at L4 norm if you want to have progress. If you look at L2 norm, there is no hope for progress at all. The other thing is exactly something that I didn't say explicitly, but what we were doing when we perturb our problem, we are also perturbing the central path. Okay? So the idea is that if you look at central path, it doesn't matter, which central path you are following, as long as it gets you to optimum. So what we really were doing, and I didn't really highlight this, but this is what really is happening behind, under the hood, is that whenever we don't like our central path, we are perturbing it to get something better. Okay, so essentially we are changing our central path whenever we don't like it, and that's I think something that doesn't show up. And also the other thing that's important is that if you ask, and that's one of the barriers why we are stuck at square root of m for general relativity, that if you ask me, you are somewhere on the central path, and you want to take a step, how big of a step you can take? Well, in the worst case, answer is square root of 1 over square root of m. But just probably. Yes, we just have seen some examples that I alluded to that. Probably you cannot do better. But the whole point was showing that, okay, sometimes some steps are bad, but then some steps are good. And somehow having the non-local convergent analysis, which again, is happening in some papers, but not really that much. So I think people are trying to understand, like, there is this kind of, understanding that we should locally always, like, a lower bound this height of the step for, general setting, which is not impossible. And that's something to think. And the question is, can this lead to actually breaking this m to the square root of m barrier? And actually, there is a very exciting recent work by Sitford, who are here on in Simons, who actually they also use some of the ideas from here, but also other very interesting ideas from there. And essentially, they get an improvement, like very important improvement over this band. They get an iteration band, which is just a rank of the matrix of this constraint matrix to 1/2. So the rank is always at most m, but sometimes it's smaller. And in particular, by using the technology, that's exactly how they got this result when they get better sparsity elements for the max flow. When they went essentially from m to the 3/2 to m squared of n. Okay, and that's exactly this is exactly the side of what they captured was this difference between m and rank of n. Okay, so. Yeah, and you already heard that from John. I guess I don't have to, and I don't think I have to explain, like, sort of convince you again. It's really important, to try to combine combinatorial and linear algebraic tools. I think that there is a room for huge interaction. We already have seen some examples when it helped, but it's really easy. This I actually should be sure. Okay, thank you.
So Dash and Spielman also were able to get in the same time min-cost max flow.
Yes.
Can you do min-cost matching?
No.
Better?
No. Like the problem is that well, there's a few problems. Okay, I didn't think about min-cost matching actually. Like the problem is that still, whatever I already used this, that I am preparing my costs. So this is a bit. I would need to think. What happens to min-cost matching when you perturb the cost? So I'm not sure. Definitely for min-cost max flow, I can do it. For min-cost matching, I think also I can do it, but I would need to think why I can do it. Like one problem is that you are having this perturbation in cost, which might be much more significant when the costs are arbitrary. Okay? Because maybe some costs are very small, and then when you add some fixed additive factor to it, additive term to it, they will completely change, breaks the problem. But okay, I definitely don't claim I can. Maybe I can, but I'm probably skeptical. So probably not.
Traditionally, we can beat up the speaker with extra questions offline afterwards. Thanks very much, Dave.
I don't think it's doesn't do you can't do what you do with something that does.
Oh, okay.